we ready to go? So, kind of in a similar vein of some of the other talks, I did a site visit with Jeff, who some of you may know, earlier this summer, and we decided we were going to throw an SDR up at one of his sites. John and Willem got wind of it, and it turned into a way of doing what John is doing, but hopefully cheaper, less, maybe 2 less zeros. So that project isn't quite baked yet, but Willem told me I was talking about SDRs anyway. So we're going to do a little bit more of a how they work and what they are than applications. But what's more nerdy than math, right? Says the math professor. So quick disclaimer, though. I'm going to try to teach signal processing in half an hour. I'm not sure it can be done. So it's going to be pretty hand-wavy. We're going to lose a couple factors of 2 here and there, but automatic gain. It'll be fine. The point is really to understand what SDRs are, not get the details right. I'm not a math person anyway. I took college classes on this like 10 or so years ago. It's been a while. So some definitions. Radio, device for converting magic to data. It's probably clear by now I'm a computer scientist, not a double E. Magic, something I'm not going to explain today. Lots of that in RF. SDR, device to make a computer do the magic instead of expensive boxes of smoke. And imaginary numbers, also magic, square root of -1. That'll come up in a bit. So radio for the computer nerd. We have a box of magic smoke. It's connected to an antenna. The antenna captures signals. Magic smoke does its magic. And we plug it into an A to D. Chris showed you an example of an A to D earlier, those signal link devices. And then we get some bits in our computer and we can do something with them, or audio, or whatever. So SDR, we take the box of magic smoke, we plug the antenna directly into the A to D, and we do all the processing in the computer. Pretty straightforward in a way. Of course, Nyquist says that if we want to sample our antenna, measure a certain frequency, we have to sample at least twice as fast. A to Ds that are that fast can get expensive for VHF or UHF or on up. But we can use a little box of magic smoke, add a mixer, down convert to a frequency we can actually A to D. And I'm only going to talk about receive, but you can obviously do all this stuff in reverse if you so desire. Transmit SDRs are a little less common and quite expensive. I know there are a couple companies that your ICOM 7300 is probably the best commercial example at the moment. That said, in the real world, if you do want to just do the simple thing, capture the whole spectrum, HF is kind of, well, not that high a frequency actually. So you can pretty easily buy or borrow on the web, which is really cool, an SDR that will grab the entire HF spectrum and let you process it as you see fit. Of course, 60-ish megahertz of samples is quite a bit of data, so they include an FPGA to do the math. And then that allows us to use a cheap computer instead of a very, very fast computer. But if you want to play with one of these without spending any money, and whoops, rx.qesdr.com. They're all over the country, all over the world. They can do some of this direction finding stuff even. At HF, direction finding is more of a what country is the transmitter in, not what block is it in. But it's still pretty cool. Everybody has supply chain issues. That's why you borrow someone else's on the web. That's really the nice thing about that software. So SDR, practically speaking, kind of like a traditional radio, we're going to take a VFO, mix it in with our receive signal, and then do everything else in software. So sounds cool. How do we do this? There are some very, very cheap and very, very small. So, John's talking about $4 grand of hardware. I'm talking about $50 of hardware and little tiny things. You could conceive of building John's thing with 4 of these and some very clever software. Clever software being the hard part, obviously. I think I can do it down to this room, but I don't have a demo yet, so that's next year's talk. But you can get on Amazon, buy one of these things. So these are called RTL SDRs. They're based on a European TV tuner design. It turns out that the TV tuner rather than implementing anything in hardware, they did the cheap thing. They built a generic radio and some clever software. And we can abuse the generic radio to pretty much receive DC up to about 1 gigahertz. Depending on the filters on your TV tuner, that may work more or less towards the edges of the range. But these no-elect guys, like the one I have here, have done some improvements, so it's a little bit less a TV tuner and a little more generic, but not much more expensive. I know I am presenting on a Windows computer, so I can scribble on the fancy tablet screen, but we're going to assume you're Linux users because it makes everything easier. It makes this sort of thing easier. I don't know if John has a mic, but he's kibitzing. We do need to disable the TV tuner drivers so that we can access it with software that treats it as a radio. So we just turn those off. And these slides, I'm sure, will be posted, so if you want to do that. Well, the ones that are posted are old. Willems, for telling me I need to give this talk like a week in advance. How about that? Some software. So the SDR world, there are a few different libraries for getting the data off your SDR and doing things with it. The SOAPy SDR stack, the RTL SDR folks have their own software. Install a couple things. If you just want a fancy radio receiver, I like this tool called GQRX, but there are a handful of others. SDR Sharp, Angel SDR. It runs on everything natively. Runs on OS X, runs on Windows. User-friendly enough. But since we want to know what these SDRs are actually doing, we're not going to use any of these fancy pre-baked tools. I'm going to use a programming language called Julia, but we're just doing complex math. So complex in the imaginary numbers sense, not in the it's hard sense. Well, maybe both. So you could use whatever you want. Anyway, let's write a receiver. But first, let's review some high school math. So if you have a signal, it's probably going to be made up of sine waves. Depending on what you're taking the sine of, you can add some scalars and manipulate the frequency. If you have two sine waves and you multiply them together, you get the sum of them and the product of them, a little bit out of phase. And that's pretty much all the math you need to write a receiver. It's actually not that hard. But when we talk about radio, everybody likes to talk about frequencies. We're receiving a frequency, right? Well, what does that really mean? Turns out you can convert between time domain signals and frequency domain signals pretty easily. This Fourier guy, dead mathematicians category, right, says that any signal is a sum of probably infinitely many, but more than one usually, sine wave. And we can convert back and forth. So we can get a list of the sine waves to represent our signal, or we can get the voltage over time. And they're pretty equivalent. Fourier transforms, of course, are magic. So if you are interested in how they work, I can probably find you a textbook to look at. We're just going to use a software library. Everybody uses one called FFTW, fastest Fourier transform in the West. And of course, the Japanese had to have an FFTE because computer people are silly. So for the visual learners, we have a sine wave. We pick some time points, and we take the sine of them, and we get a sine wave, right? If we tweak the frequency a little bit, or the scalars that we're taking the sine wave of, we can get a higher frequency sine wave. So how does this kind of apply to frequency domain, right? If we have a sine wave at a particular frequency, we can take the Fourier transform of it, and we should get one point at that frequency. Why do we have a big triangle? Well, because the plotting software is trying to do linear interpolation, and making the plotting software do the right thing is hard. Again, with the week of warning thing. But you get the idea. So we'll just pretend this is 1 point, and that'll come up again in a second. So if we want to shift our data around on the carrier, we use a mixer, right? And you do that if you had a traditional hardware radio. But we can do it in software as well. So if I make two sine waves in the same way we just did, and I multiply them together, I get, in the frequency domain, 2 points. And they're bigger triangles because the scale on the x is different. So again, it's really 2 points. Just take my word for it. But we have one that's the sum and one that's the difference. If we were using this for mixing, for radio, this is fine because we're probably only going to have enough data to represent one side or the other. So even though we have the sum and the difference, we'll just throw away one of them and pretend like it's what we want. It's a shift. Back to SDR. So if you want to do some data processing with SDR, you can use one of those fancy GUI applications and listen live, do the decoding in real time. But we want to know how this works, and doing things in real time is hard. So we're going to leave that in the magic category, and we're just going to do a recording. So there are a couple different tools depending on the SDR you have. If you have something like a HackRF, then there's a tool that is specific for that SDR. Here we're querying the SOAPy SDR framework, which is kind of a generic abstraction layer. And we're just going to grab the whole 2 meter band plus a little bit. And this is something that's really cool about SDRs. If you have a fast enough A to D, I can capture the entire 2 meter band. And if there's 2 or 3 nets going on at 6 p.m. on the weekday, I can listen to all 3 of them at once. And that's fantastic, right? But even more than that, I don't have to know what I want to listen to in advance. Maybe I don't know what signals there are, so get them all. So for the sake of this demo, I'm going to get roughly a 6 megahertz chunk of spectrum centered around 144 megahertz. And I'm going to let the software figure out what format to give it to me in. Turns out the default for a lot of SDR applications is 8 bits per sample, complex numbers, and interleaved IQ. And we'll talk about IQ right now. So the SDR world likes to represent the signals as a sine wave and a corresponding sine wave 90 degrees out of phase. I'm told this makes the math easier. Willem is one of the people who's told me this makes the math easier. It actually does. But explaining why is probably a little bit much for this talk. It does give you the ability to measure things like phase changes relatively easily. For now, one of the common representations of this is as a vector in the complex plane. The details of that are not important. It turns out, though, that if you structure your math in a certain way, everything just works nicely. And I'm just going to leave it at that for now. If you're interested in more, we can talk math. But anyway, what did our RTL SDR actually give us? It gave us integers, signed integers. So the high bit is the sign bit. Everything is in what we call baseband. So I have a dial frequency, right? And we set that dial frequency to be 0 in what comes out of the SDR. And everything else is an offset to that. Of course, since 0 is the center frequency, we now have negative frequencies, which are not really a thing. This is where the imaginary numbers come in. Kind of a just go with it situation. Don't think too much about the physics. It does make the math work really well, though. We do need to keep track of all this ourselves. The SDR just gives us a big list of numbers. So we've written these to a file. So we need a little bit of code. We basically read them in from the file. And the interesting math here, we take our number and we split it in half because the highest bit is a sign, so positive, negative. And basically map these into complex floats to make the math easier. You can do this in integer math. Integer math is hard to get right, but you don't lose precision. But we don't care because it's audio. So we're going to go with floats. Of course, looking at a big list of 6 million numbers is hard. So let's just plot it. So in the frequency domain, we notice a couple of things. The big thing you notice is that we have a big energy spike around 0. And it turns out that's an artifact from the way the SDR does mixing. Math does funny things at 0. And you're looking at the energy from your VFO, basically. So that signal's not really there. So what we do in the SDR world often is we do something called offset tuning. So if you're using one of those GUIs and you're trying to listen to a signal, you probably don't want to tune your SDR right at the signal you want to listen to because there's this artifact there. Tune it a little bit off to the edge, and then you want to do in software a shift and listen to the signal you actually want. So When I was recording this, this is also me just keying an FM transmitter at 146.54, so well off the edge of the center. It doesn't really, I mean, you don't have to be very far off to avoid this artifact, obviously. And then there's a whole bunch of background noise, because that's the story of my radio life. So obviously, the first thing we want to do is tuning. And we showed that if you have the product of two sine waves, you get their sum and their difference. So what we want to do is slide the signal we're interested in over 0. And then that makes filtering easier. So what do we do? Well, we take another sine wave and we compute a sine wave at the frequency that is the difference between where the signal we want is and where we want it to be, and we multiply them. So same thing we did with the simple sine waves earlier. And so we generate a sine wave. This is probably doesn't show on the screen very well, but we do a pointwise multiply and a little convert to dB and convert to the frequency domain. And you see that our signal that was on the right has now moved to the middle. And because we're in the complex plane and we're trying to plot on a real graph, real graphs are easier to look at, you notice that the center is actually around 3. That's because I captured 6 megahertz of samples, and 3 is now 0. So again, with making the plotting library do the right thing. Didn't bother. So 3 is 0. Again, go with it. You also notice that the artifact that we were interested in earlier is now a big negative frequency, and so we'll just throw it away in a minute. It's no longer an issue. Of course, we have captured a lot of data. At 6 mega samples a second, we've upconverted them to 32-bit floats. We're in the gigabyte plus range of memory. Luckily, modern computers are really, really fast. But filters are expensive. So the good news is we actually only care about maybe a 25 kilohertz if this is FM chunk of spectrum. We've selected the part of it we're interested in. We've slid it to 0, so we can just throw away the rest. And that's kind of a theme here. If you were interested in maybe 2 signals, you'd have to keep all the data so you could pull out multiple signals. But if you're only interested in listening to the radio, then we're going to take and throw it away. But again, Nyquist says that we need twice as much data as the chunk of spectrum we want to listen to. So, ideal world would keep 50 kilohertz. But it turns out that a lot of audio libraries like 48 kilohertz. So close enough. Keep the 48 kilohertz. So we loop over our array of samples, and we throw away most of them. We keep 1 out of 128 in this case. And if we plot the spectrum again in the frequency domain, we notice that we have our original signal still here, which is good. And we have some artifacting, which is less good. And that's just because we're kind of sort of capturing the high frequency components, right? And lots of noise still. You will notice that we have 20 dB of just background noise. One thing you'd do if you were doing a real receiver and not a demo talk, you might want to remove DC offsets. You might want to kind of clean that up a little. But it doesn't matter because I didn't assume I'd have audio out, so I'm not going to do a demo. Filtering. So since we have our data around 0, we want a low-pass filter, and it's a symmetric low-pass filter. We're going to low-pass filter the negative frequencies and the positive frequencies, if that makes sense. So we have 25 kilohertz, but we have 12 positive kilohertz and 12 negative kilohertz. Again, just go with it. Negative frequency, it's fine. You could also think of this as a bandpass filter if you prefer. There are a lot of ways to do this. I'm going to talk about finite impulse response filters a little bit. Obviously, we have a finite amount of data. We have finite frequencies. We're able to represent finite frequencies. So finite filters make sense. This is pretty directly comparable to a duplexer if you were in the physical hardware world. But those are expensive and kind of finicky to tune. You could also imagine just taking your signal and throwing away chunks of it in the frequency space and then doing an inverse Fourier transform. But that's equivalent to an infinite filter. And funny things happen at the edges because you're assuming that the signals are actually infinite. So there are ways of handling that, but math is hard. So what do we actually want? Well, we want basically a rectangle in the frequency domain. So one way you could approach this is to draw a rectangle and then take the inverse Fourier transform of it. If you do that, you get a squiggle. If you look this up as the continuous domain, infinite precision world, it's actually a sine C function, which is supposed to look like this. But finite precision math, finite sample rate. Yes, I cheated. I looked it up in my signals textbook. But luckily, this is a pretty easy thing to compute. It looks like that. So we pick a cutoff frequency, and we compute some things that are usually called taps. Basically, the idea is you create an array of, not really samples, but numbers, that you then do a convolution with your signal, sort of a multiply, but not really. Kind of walk along the signal, multiply by this thing, sum up the results, multiply by the next, sum up the results. And through magic that's kind of hard to develop an intuition for, it throws away only the part of the signal that you want to throw away. More taps gets you a sharper filter, so you can imagine more cans in the duplexer. Of course, in the physical world, that means you need a bigger thing. In the computational world, that means more math. So there's a trade-off between kind of sharp edges on your rectangle or computational efficiency. There are a ton of, this is a really deep topic for designing these filters. There are a ton of different approaches. You can basically do the inverse Fourier transform thing I did, but it turns out the math for that is really expensive, so there are better ways of doing it. But in an ideal world, you would end up with something like this, where we have almost no signal except in the middle, where we wanted it. And now, you still get a little noise because finite math and whatever. But that's your signal. If we're doing AM, that's your signal. Throw it out the sound card, listen to it, be happy. Success. For sideband, maybe you want to tweak the filter a little bit, shift it off to the side so that we're actually rejecting one of the sidebands. Success. For FM, well, FM's a pain. FM, we're actually interested in the change in phase, how the frequencies are changing over time, not the amplitude per se. Turns out that because of the way we're representing this, that math is actually pretty easy. You look at the angles between the I and the Q. But not going to worry about it too much. For digital, well, people do all sorts of things. Often it's something on top of FM. But the nice thing about SDR is if you want to decode some arbitrary scheme, it's just software. I don't have to go build a chip to do this, at least. So if you want to do it fast, you should go build a chip. That's what programmable logic is for. Then you can program your chip, which is actually very commonly done in SDR. Many of the higher-end SDRs will have an FPGA on the board so that you can do at least some of this processing in hardware or in software-defined hardware. Noticing a pattern here, we can software-define all the things. Cheaper to prototype that way, and you don't have to wait for DHL, to pick on an earlier talk. Other things you might want to do if you were to write a software-defined receiver, some sort of gain, volume control, maybe. Squelch, makes it easier to listen to. Most radios these days do some extra DSP voice processing to make you a little easier to understand, at least in theory. All of these things can be done in software. It's just more math and trying to keep this talk short-ish. Anyway, why would you want to do this? Well, learning about math is fun, sure, right? The room is disagreeing for those who are remote. But you can play with new modes. Do I need a DMR radio, a P25 radio, a D-Star radio, and a Fusion radio? Yes. No. I need 4 pieces of software and 1 piece of hardware. Much cheaper that way. And yes, there's software for most of those available for free on the web. There's some patent encumbrances with the various digital voice radios that make that legally sketchy, but the software does exist. And I believe those patents are expiring in the next year or so, so it should get a little bit better. Certainly, it's cheaper to buy one piece of hardware and then a bunch of free software on the web. Decode something interesting. Decode all the interesting. If you have a big chunk of spectrum that, maybe people are talking on different simplex channels. I know here in Colorado, we've decided that the 2-meter calling frequency is no longer cool, and we're going to shift up 40 kilohertz to an adventure frequency. Maybe you want to listen to both and see who's adopted each one. It's certainly cheaper than buying the hardware to listen to all the things at once with all the different protocols. And this talk, of course, was motivated by something called TDOA, time difference of arrival. So Willem and John got wind that I was playing with SDR a little bit, and that TDOA was a thing people did with SDR sometimes. I got a call the next day from John, extremely excited that maybe we could use SDR to replace his extremely expensive Doppler equipment. Kind of a work in progress. There's been some research done in that direction. Anyway, the idea behind TDOA is that if I have radios at least 3 sites and a really good time synchronization between them, I can measure the difference it takes to arrive, my signal of interest takes to arrive to each of the 3 sites. If I know how far apart the sites are, I should be able to calculate exactly where the signal came from, give or take multipath. Of course, we'd need really good clocks for that. So I think the trick is going to be we need another reference transmitter at another known site that we can use. Since we know the distance between our known transmitter and our receivers, we should be able to figure out the time delays between the different receivers and calculate exactly relative what time it is, and then based on our signal of interest, figure out where the signal comes from. There's a guy in Germany that did a little research on this and came up with a proof of concept that gets to about the block level. But playing around with some of these newer SDRs with better oscillators in them, I'm guessing I can get it pretty much down to room-sized resolution. Soon. Yes. The trick with this is that radio signals propagate kind of fast. So a couple feet is a couple nanoseconds, maybe. So we're talking about time accuracies in the handful of nanoseconds range. So things like how warm the oscillator in your SDR is start to matter. On the other hand, you're doing all this processing out of band. You have a good reference signal, and it doesn't really matter how precise the reference signal is as long as it's the same and they're all receiving it. So there's no reason this shouldn't be doable. Of course, my signal processing skills are not the best, but I think we'll get there. And you don't need to. That's the thing. You just look at when the reference signal starts. So all you need is a tone, and you look at the edge. You just need an energy pulse at a known location, and then you measure when it arrives at each site. And since you know where the known location is, and you know relative where each of your receivers are, you can calculate the difference between the times and the receivers. It would help. Yeah, so that's an unsolved. We'll see how bad that is. The better the oscillator in your SDR, the more likely this is to work. But I'm not the only one trying to do this, and there are some other applications that are also motivating really high quality SDRs. Some folks are doing atmospheric or space type research with this that needs really precision frequency accuracy. So I think the hardware is there, and I think the hardware is there in the hundreds of dollars, not in the thousands of dollars. One catch with this is that you do need to be able to see your reference signal and your signal of interest in kind of the same blob of data.
When you say space things, a while ago, some folks got together here in Colorado and were trying to figure out how to do locations of spacecraft sitting on the surface of Mars when you don't have GPS signal.
Yes.
And this is what they came up with. And they got past me when there were more letters than numbers in the formulas. So I had to call Willem.
Math doesn't involve numbers.
It's just letters.
It's things that
I don't
represent
do letters.
numbers. It doesn't have to be letters either. You can use hieroglyphics or symbols or...
I'm a journalism major. I don't think in numbers.
I don't either. You just move the letters around until it represents what you want. I like it. With that in mind, if you're not a programmer and still want to play with this, there's a really cool project. Some of the developers are actually in Denver, called GNU Radio, that has a flowchart-based programming environment. So you get blocks that implement some of these primitives that I'm talking about, and you wire them together on the screen like you would a circuit, and get kind of the equivalent output. And there are ways of doing graphing and all these things. So if you want to play with this, but you're not a programmer, I highly recommend you check out GNU Radio. Email address for the record, but I want to throw up this slide instead. Guy on the other side of the planet did a very similar talk to this. Actually has a demo proof of concept receiver you can download, but it's written in C, so less fun. MathWorks wants to sell their programming environment, but they have a very good book on SDR. And is, I think, one of the more readable references. Likewise, the PySDR library has a very good description of how IQ works and how some of this math works to help you use their library. Already mentioned GNU Radio, fun blog that talks about basically all the software. So people like to write decoders for things. You know, you want to track aircraft above your house, write a decoder for ADSB. You want to track hams, write an AX25 decoder. So this blog kind of tracks all the latest and greatest software. So it can be a fun read too. Anyway, I will try to entertain questions, but this is not my field by day. So, or it's too much math and no one has any questions. That's cool too. Right, WebSDR.
Right. Supposedly, I haven't looked into this myself, but I heard somebody the other day talking about WebSDR has a TDOA decoder.
That's the Kiwi SDR, yeah. They're doing it with a proprietary web server. So the idea is that you get samples from your SDR and at least 2 other SDRs. It goes into this magic web server that does magic, and it tells you where your signal is, which is super cool. But the Kiwi SDR is HF only, so it doesn't help John with his jammer problem. And they're doing GPS-based timing, so the Kiwi SDR has a GPS on board. But HF, you've got things bouncing around the ionosphere, so the accuracy is same county, not same building. Still very cool, though. And you mentioned WebSDR, so RMHAM has been deploying WebSDRs at a few places around the Front Range to play with this and other things. I know Jeff is using it to diagnose PA problems on some of his repeaters. So this one's running at West Creek, south of here. And if you're on the RMHAM backbone, which probably people in this room are, but not in general, you can connect up to this and, oh look, something just stopped transmitting. Oh, that's a bummer. I don't know why that is. Yeah, so that's what it looks like. The WebSDR software, this is running on a Raspberry Pi tucked in the bottom of a rack. It actually has 2 different receivers connected to it, so we can pick whatever frequency we want. And a lot of these SDRs are very wideband. We weren't sure how this was going to go at a radio site because you have a lot of noise. And traditional radios, you'd put a front-end filter on. You can't do that here because you're trying to receive from DC to 2 gigahertz. There is no filter. But it actually works really well. And the antenna for this particular device is a piece of twin lead that we found lying around in the trash can and strung on the tower. And it works really well. And this software can decode all sorts of things. FreeDV is a competitor to that proprietary digital voice codec I mentioned earlier. DRM, HD radio, it'll decode CW for those of us no-code hams. If you want packets in here, if you've got a pager, the JTK protocols, you name it, it's in here pretty much. And you tell it what protocol you want, you find an interesting looking signal and click on it, and I probably don't have audio hooked up, but that's all there is to it. And this is doing the same math we just talked about. It's doing some of it in your browser, and it's doing some of it in the Pi at the site. But this is really nice. Those of us with a terrible RF noise floor at home can log into this radio somewhere else that's hopefully better and still listen, which is great. So we don't have real good long-term plans yet, but I want to get this exposed to the web at some point. There's some challenges with that. Mainly, it's a Raspberry Pi. It's not super fast, but we'll get there. Other questions?